Okay, for the final part of today's lecture, the last thing that we'll be exploring before we get on to some modelling of the carbon cycle, we'll be trying to develop an understanding of the difference between a positive feedback and a negative feedback. So thinking back on our glacial, interglacial cycles in atmospheric CO2 here. So here, time at the present is on the left side in this diagram, and the past deep time is on the right-hand side. So time is going forward in this direction on this particular plot. What we notice about the ice core records is that they reveal these relatively stable CO2 levels during the interglacial periods, and possibly also some glacial periods. So you'll recall that we saw that during the interglacials, the CO2 levels in the atmosphere often come up to around about 280 ppm, and then they drop down again to about 180 ppm during these glacials. And in some of these periods, you can see that there are quite stable levels in the atmosphere, only varying by a few to a few tens of ppm over very long time periods. So this is an extra long interglacial period that lasted around about 30,000 years, 400,000 years ago. And you can see the tops of these slightly colder interglacial periods here are also very stable, as well are some of these glacial periods. And what we notice is that between these periods that the CO2 levels in the atmosphere tend to decrease slowly into the glacials, so the deep glacial periods when it's really cold, and then they bounce up very quickly at these terminations, what are known as terminations of glacial periods, back into very warm conditions. And so these terminations happen over relatively short periods of time, of only a few thousands of years. And so what we have here is we have this idea that we have steady state during these periods, and then we don't, but most of the time we don't have a steady state. In fact, CO2 levels in the atmosphere are going up and down rather rapidly a lot of the time, so we don't have steady state. And the question is, why might that be? So at this point, we're going to introduce the idea of concepts of positive feedbacks and negative feedbacks. So one needs to really understand this, try and understand this as well as you can. A positive feedback is a system response to a positive or negative change that makes that change larger. It amplifies the change. So an example of that, and an example of a positive feedback, would be an increase in CO2, atmospheric CO2 levels, enhances the greenhouse effect. This then warms the ocean, and it results in outgassing of CO2 from the ocean to the atmosphere, and that additional CO2 increases the level of CO2 in the atmosphere further, and so we end up actually going around this loop here. So if we have a small perturbation in the first place that increases CO2, we keep on going around the loop and it gets amplified. These processes, the warming of the ocean as a result of the greenhouse effect, and then the decreased solubility of CO2 in the ocean when it's warmer, results in yet more CO2 being released into the atmosphere. So an alternative to that is if we have a decrease in atmospheric CO2, that reduces the greenhouse effect, which cools the ocean, which then results in absorption of CO2 from the atmosphere into the ocean, and we have CO2 then decreases in the atmosphere. So again, you can see that's a positive feedback where the initial decrease in CO2 is amplified to produce an even greater decrease in CO2. So that's a positive feedback. That's a positive feedback loop. A negative feedback is a system response that reduces a change, making the change smaller than it was. So this actually stabilizes the change. So there's something occurs that would, say, increase the amount of CO2 in the atmosphere, then there would be a set of system processes that actually result in that decrease being damped or stabilized in some way. So here's an example. So we have an increase in atmospheric CO2, enhances the greenhouse effect, which in turn promotes growth of the terrestrial biosphere. So warmer, wetter, more CO2 available for photosynthesis, promotes growth of that terrestrial biosphere, and that terrestrial biosphere draws CO2 out of the atmosphere, and as a result, CO2 reduces in the atmosphere, so, which is the opposite to the increase that was produced here. So this particular mechanism or set of processes is a negative feedback loop. It's a system response that reduces a change, making it smaller. So these are stabilizing, negative feedbacks stabilize systems and result in a tendency towards steady state, whereas positive feedbacks amplify changes in the system and promote more change. So when we take our glacial periods, we might propose that positive feedbacks appear to dominate much of the time. So positive feedbacks are amplifying the change. So once we start going down here, we keep on going down, we get amplified changes, and then they have come back up again. So the system is in change and it's responding to other changes in the system, and those changes being amplified. Whereas negative feedbacks, we might propose, would dominate during these interglacial periods and also the glacial periods in some of these glacial periods. And under these circumstances, these negative feedbacks dominate and we end up with more or less steady state conditions for significant periods of time. So to give you an idea of some other examples of positive feedback, so here we have positive feedback. We would have, so as Luigi in one of the lectures in the atmosphere module, Luigi taught you about changes in insolation due to the changes in the elliptical orbit of the Earth relative to the Sun. And so those changes in insolation occur at different times of the year and at different latitudes. And so an intensity of summer insolation at high northern latitudes. So if that's reduced, then we get growth of continental ice sheets, which then result in an increase in the planetary albedo. So those ice sheets reflect more energy back into space, which then cause a reduction in global mean temperature, which then results in further growth of continental ice sheets. And so we go around the loop. So we have an amplifying mechanism through this set of processes that represents an ultimate response to these relatively small changes in summer insolation at high latitudes in the northern hemisphere, where the continental ice sheets develop and grow. So another example of that is here, where in response to those insolation changes in the same way, we have, have global mean temperature decreasing as a result of that mechanism. And as a result of that, we have the atmospheric CO2 solubility in the ocean increasing, so more CO2 gets drawn out of the ocean out of the atmosphere into the ocean. And so CO2 goes down in the ocean, and through the greenhouse effect, we have a reduction in global mean temperature, and then we get growth of continental ice sheets, planetary albedo, and we go around the loop here again back to global mean temperature, and then we also have this little loop here, so that the reduction in CO2 reduces the global mean temperature, which causes further reduction of CO2 in the atmosphere because of the solubility in the ocean. So there's some examples of positive feedbacks and feedback loops within the Earth system. So now back to the question we were going to, or we're trying to answer, which is, how long will anthropogenic CO2 remain in the atmosphere? And there's a significant question here in regard to, or with regard to, positive or negative feedback effects. And it just so happens that if positive feedback effects dominate, then we could end up with a runaway greenhouse effect and an uninhabitable planet could result. So these are the sorts of things that when people talk about tipping points, some of these non-linearities in the global climate system, and also these runaway effects are the things that people are talking about. And our understanding of some of these positive and negative feedbacks, or the complexities of them, actually make the modelling of the whole system rather complicated and challenging to predict exactly what might happen. Anyway, so let's get on with what we're trying to do. So what do we need to do? We need to have an estimate of the size of the anthropogenic perturbation to atmospheric CO2. So this is our excess CO2 that's in the atmosphere due to anthropogenic CO2 emissions from burning fossil fuels, taking carbon from the geosphere and burning it and putting it into the atmosphere, and from there it gets distributed around the other carbon reservoirs. So let's get our estimate. So we're looking at the CO2 increase relative to the last, so here's the last 10,000 years, which is the last interglacial period. So you can see it's varied a little bit over this period, but it's generally been around about this 280 ppm level, particularly in the latter part of this, this Holocene period, or the last 10,000 years. So the amount of CO2 as mass of carbon in the pre-industrial atmosphere during this time was 600 gigatons. And we can calculate that for, at the present, where we have now in excess actually of 410 ppm, we're up around 415, 600 gigatons times 410 minus this amount here, 280, divided by 280, if we take that fraction and multiply this, we estimate this as being close to 280 gigatons of extra carbon in the atmosphere now. So how long would this CO2 take to return to steady state if emissions were stopped today? So to begin to answer this question and build our carbon cycle model, what you need to do, or what we need to do, is we need to calculate the residence times for carbon in the major reservoirs during pre-industrial times. And so you might be thinking, well, why calculate it for pre-industrial times? Look, simply the answer is that based on our first order kinetics, or the idea that the fluxes from a reservoir into another reservoir will be dependent on the content or the amount of carbon in that reservoir, there's a proportionality which flows through. So the residence times during the pre-industrial times should be a reasonable estimate of what the residence times are during the present time. So what I'm going to ask you to do is look at this table and calculate the residence time based on the pre-industrial carbon stocks in each of these reservoirs, and then take the input or the output flux, it really doesn't matter, calculate the residence time of carbon in that particular reservoir. So I'll leave that for you to do, and that'll be preparation for the tutorials on Thursday, where we'll actually use these numbers to generate our carbon cycle model. But before I finish up today, I'll just show you the sorts of things that we'll be doing after. I'll show you some of these calculations. So the residence time of carbon in the atmosphere with respect to the surface ocean. So this is the amount in the atmosphere relative to the flux out of the atmosphere. You can calculate that to be about 8.5 years. So the residence time of carbon dioxide in the atmosphere is about 8.5 years for the atmosphere with respect to the surface ocean. Now you can also calculate a different residence time with respect to the terrestrial biosphere. And if you make that calculation, you can see that it's about 5 years. And on the basis of those sorts of exchanges, one can estimate that, well, the average time that a CO2 molecule would spend in the atmosphere is actually really surprisingly short. It's only of the order of, it's going to be somewhere between 5 and 8.5 years, which I think is pretty surprising. The other thing you might notice here, and I think this is really important, is that our total fluxes from anthropogenic emissions are actually really quite small relative to these other annual fluxes between the reservoirs. So these other fluxes really dwarf the amount of carbon that's being emitted from fossil fuel burning, for example. In fact, they're almost 15 times larger in regard to the terrestrial biosphere exchanges. So here we have this roughly 120 gigatons of carbon flowing back and forth, almost in balance between the terrestrial biosphere and the atmosphere each year. So these numbers are actually really quite tiny, but normally the system is in balance and it's close to steady state, and it's these relatively small, I mean, it is 10 gigatons of carbon after all each year, but they're enough to perturb the system and grow the amount of CO2 that's in the atmosphere. If we add these two together and we actually look at the residence time with respect to the perturbation, what we find is, so this is now looking at the excesses. So if we look at the excess, remember how we did this with the hydrological cycle. So the excess amount of carbon dioxide, or carbon actually, in the atmosphere is in this diagram back in 1995, it was 165 gigatons. And the balances of the fluxes in and out, so here we have the balance of the excess fluxes in and out between the atmosphere and the ocean, and then between the terrestrial biosphere and the ocean. They add up to 3.2 gigatons on average per year of CO2 are actually being taken out of the atmosphere and put into a combination of the surface ocean and the terrestrial biosphere. So we have, in this diagram, we've got 8 gigatons of carbon as anthropogenic emissions into the atmosphere each year, but around about 3.2 of those 8 gigatons end up going back into the terrestrial biosphere and the ocean each year. And if we calculate the residence time for that excess carbon, we get a number that is around, so it's 165 divided by 3.2, and we end up with about 50 years. And that would be the number that we would then use to calculate the time period over which CO2 would be drawn down back out of the atmosphere. Hopefully that makes sense. The only thing that I would say is that is that now with the current estimates of, so this number up here is around about 280 gigatons now. If we redo these calculations, I don't have up-to-date flux estimates, but based on that number, we might suggest that this residence time has maybe increased a little bit, and it's up around 70 years now. So if we plug those numbers into a calculation, and we said we suddenly, and in this calculation, we stopped emitting carbon dioxide into the atmosphere in 2015. So this is just a model. So here we have carbon dioxide going up in the atmosphere to 2015, and then we stop the emissions at that point, and we then let them reduce according to that residence time. We have an exponential decay like this back down towards the original value, which was pre-industrial value of 600 gigatons. So here's our emission curve coming up and then going down if we turn off emissions here. And what you can see is that in this little model that I've built, and we'll be building a more complicated and better model than this, you can see that the amount of carbon dioxide in the ocean is also going up because some of it's being transferred out of the ocean, out of the atmosphere into the ocean, and then that continues to go up because the ocean takes up CO2 from the atmosphere gradually over time. So this CO2 that was in the atmosphere is being distributed around the other reservoirs in the system. It's being distributed into, being taken up and sequestered by the terrestrial biosphere and by the ocean, and in particular by the ocean. So this is the sort of trajectory that we might sort of predict based on a simple residence time calculation. So that's for a simple ocean atmosphere model. If we take that one step further and we still use our residence times that we calculated, that we can calculate from this diagram, but we also include these exchanges between the surface ocean and the deep ocean, where much of, where the vast bulk of the carbon is actually stored, we get trajectories like this. So on the left, we have the atmosphere in blue, and we have the surface ocean in red. And I've started the surface ocean here at 1,000 gigatons. This is a slightly different model, but slightly different starting number, but it actually really doesn't make much difference. So if we turn off our emissions in 2015, instead of a simple exponential curve, we actually end up with this much steeper part at the beginning, which represents uptake into the ocean, into the surface ocean. And then after a number of decades, what happens is that carbon in the surface ocean starts to be transferred into the deep ocean gradually, and you can see the response of the deep ocean here, numbers on the right. The amount of carbon in the deep ocean goes up like this over a very long period of time. So this is over the next 500 years. And you can see that in the end, the atmosphere returns almost back to its original starting point, as does the surface ocean. And the vast bulk of the added CO2 that was added back here before we stopped the emissions gets distributed or gets taken up into the deep ocean with time. So again, this is a model based on these simple residence times calculations that we can make. Now, the interesting thing about those, and we'll be comparing the interesting thing about that, and we'll be comparing the model that we build in the tutorial, is that these simple models actually compare quite well with supercomputer models that take into account all the feedbacks in the system. So here are some models, supercomputer models for different levels of CO2 emissions. going to much higher levels. And then if we go to much higher CO2 levels, you can see that the amount of the concentration in the atmosphere goes to much higher levels when we emit more, and it doesn't respond as fast. So if we emit less, we end up with lower amounts in the CO2. We end up with lower amounts of CO2 in the atmosphere. The interesting thing about these particular models is they don't show the CO2 coming down, and as I'll show you in the tutorials, that this particular model isn't a great result, but these are taking into account feedbacks which tend to amplify these effects, and as a result, the CO2 tends to remain in the atmosphere. And so some of those, just to reiterate some of the feedback effects that might go into this sort of modelling, I've just given you a few more here to think about. And so at that point, that's the end of the lecture, the second lecture, and I look forward to seeing you in the tutorial. Just a little note, that being, I will put up another brief video that will go through how to do the calculations of the model during the tutorial. So I invite you not only to have a look at the question sheet for the tutorial, but also to have a look at this video, which should help you actually build the model. Okay, thanks very much. See you on Thursday.